Okay, welcome everyone to our monthly invited talk series. It's a pleasure to introduce Professor David Gotz from University of North Carolina. So David received his PhD in computer science from UNC in 2005. Later on, he also moved to be a research scientist at the IBM Watson Research Center in New York. And finally, after 2014, he moved back again to UNC, where he is now Associate Professor of Information Science, and he's leading the Visual Analysis and Communications Lab. And we're looking forward to the talk with the title Visual Analytics for Cohort Selection and Analysis. Thank you, Dave. The floor is yours.
Sure. Thank you for inviting me. So let me start the share again. All right, I think you should be able to see my screen at this point. If not, speak up. But I'll go ahead and get started. So I gotta hide the tooltip here. All right, so thank you again for inviting me. I'm gonna talk about a bunch of different projects from the last several years of my research. Many of them focus on dealing with time and how things evolve over time. So I like to start my talks with my own personal timeline, which summarizes that kind introduction from Mark. So as mentioned, I have my degrees in computer science. I went to IBM for about 10 years, and that's where I really started focusing on health-related applications of visualization and visual analytics. Then came back to UNC a few years ago, and I'm now assistant director for the Carolina Health Informatics program, which is our graduate level training program. We have master's and PhD degrees focused specifically on all aspects of health informatics. And so a lot of my work focuses on that target. Also, as was mentioned, I'm directing the Visual Analytics and Communication Lab here at UNC. And so a lot of the work you're going to see is driven by a lot of the students and collaborators you see in the pictures here. So I want to give them credit. All right, so most of my work these days does focus on health-related things, and it's really driven by this observation that medicine is a data-driven enterprise. If you think about going to the doctor when you're sick, right? The doctor observes things about you and writes them down. They try a particular medication and see what happens. They then take lab tests and gather more data. Then they write more of that information down. You leave and you come back a few months later and they write more things down. And they look back at what you did in the past and maybe try and change your medication or change your whatever intervention they're doing to get a better outcome. And this whole process, even when we had paper records, was a data-driven enterprise. As the industry around the world is modernizing, we're having these increasing use of electronic systems to manage medical data. And finally, the health systems around the world, the US has been pretty slow because of its fragmented nature, that it's not centralized. But we're finally at the point where, just like other industries, we now have large databases of electronic health information. And a lot of what motivates the work that I do is thinking about what we can do with all this data now that we're gathering it at scale and in very large volumes in very rich detail. And there's so much opportunity to use this data for doing interesting things. Now, the primary reason why places are deploying these electronic medical record systems is just to replace those paper folders, right? So data gets stored and recalled the same way it did in a paper system. So that's the base requirement, and all of that is happening already. And then the first thing that people did is realize, well, we have all this data in electronic medical record systems. We can now look at all the people who go through a particular office, or all the people who are admitted to the emergency room, or all the people who are diagnosed with a particular disease, and do typical business intelligence type reporting and understand aggregate outcomes and do that more efficiently. And so people are doing that kind of thing too. The work that I try and explore in this cohort selection analysis work is really to try and think about what else we can do, particularly if we start combining interactive visualization with data analytics, to look into this very large collection of medical data that we're gathering and try and think of ways that we can get essentially precision real world evidence in the same way that the motivating project you described that you're working with a pharmaceutical company to do. The same thing is here if we look at health systems, right? Where you might have a network of a whole bunch of hospitals, whether it's a a national health service like in the UK, or whether it's the UNC health system where we have a dozen hospitals and a whole bunch of outpatient clinics, we're still gathering data on millions of different patients, all of whom are experiencing different things. And if we can subset the data and look at it in different ways, we can start to use that real world data to drive decisions by policymakers, to help researchers, to help institutions make policies, to help doctors treat patients more effectively, and to help patients themselves better understand their health. And so with this wide range of different use cases, there's obviously a whole bunch of different visualization types of problems that we could work on. And these are just screenshots from a variety of things that we've done. But I'm going to focus today specifically on this notion of visualizing temporal event data, which is what we have in a lot of medical data, and then using that to do cohort selection and analysis over populations. And so to motivate this work, kind of from a simple example, if you think about temporal event data, so things that happen over time, like a traveler who might travel from airport to airport for a trip, we can arrange all those events that happen over time in this nice timeline for an individual person, and we can associate with it a specific outcome. So in this example, there's a person who's traveled through a bunch of different airports, and we have an unhappy face at the end. We could do the same thing for multiple patients, or multiple people, excuse me. So here's another person traveling, and they have a different sequence of airports and departures that they're dealing with, and they end up with a much better outcome. And so we can start to look for things that are different between them. For example, the first person had lots of different cities. They also had a stopover in Washington, D.C. Maybe it's one of those two things that might be leading to the unhappy face, or maybe it's just that they had a lot of stops altogether. Meanwhile, we can also look for things that are in common across them. For example, the similar period of time where people were both in the same place, and start to try and reason about associations between that common pattern and outcomes that we might be interested in. Now, this example is a pretty simple one where we have the different cities and arrivals and departures. There are only a handful of different events that occur. But if we think about applying this to the medical domain, there's a lot more stuff, right? So those timelines get a lot more complicated, where you have office visits, hospitalizations, diagnoses, medications, procedures, lab tests, and a whole bunch more, including demographics and social data, things that aren't necessarily temporal in nature. They don't happen at a particular time, but it's just an attribute of the entity, in this case, a patient. So just as a couple of real world examples from data that I work with in a lot of my research, primarily I work with the UNC Healthcare Clinical Data Warehouse, which is a system that basically archives for research purposes every day, I believe. It might be updated every week. Data from the UNC Health System, which is more than a dozen hospitals and thousands of outpatient clinicians, so people who just come in for appointments. And that data is gathered for the regular delivery of care. So every time I go to the doctor myself, I'm generating data that goes into this large archive of health data. And then that's made available for research purposes with the right privacy protections and IRB approval and those kinds of things. But that data then can start to drive various things like quality improvement or the types of research that I'm going to talk about. The other data set that I work with comes from the UNC Lineberger Integrated Cancer System, Cancer Center, which is a large cancer hospital and research enterprise. And one of the things that they maintain is a disease registry for all cancer patients across the state of North Carolina, where we have about 10 million people living in the state. And so in this data set, we have as close to 100% of cancer cases as you could get in a reasonable system, because there's a requirement that all cancer cases get reported here. And so we have data from all patients who have cancer, plus data from about 60% of the state from their health insurers. So it's about 6 million patients for whom we have a large amount of data. And this is used for all kinds of outcomes research to understand how to get people to do cancer screening tests, to kind of what the best drug is for a particular kind of cancer. And so there's a team of researchers here who are working with this data set pretty much all the time. So given those data sets, if you think of them as these longitudinal streams that capture point events over time of these millions of patients traveling through their health journey, The mental model that I try and look at is, can we treat those data points as people traveling down roads that describe the evolution of their disease? And can we use visualization and analytics to help discover what those roads are, understand which of those roads lead to better outcomes or worse outcomes, and then hopefully help people drive their decision-making to put people on the better path, even when that may be the path less traveled in normal practice of care. And to try and do this in a more targeted way than we might normally do. So if you think about typical medical evidence where you have a study, the inclusion criteria are pretty specific. They typically exclude anybody with multiple diseases because that's too complicated. So we're going to focus just on people with one disease. And we'll do a gold standard clinical trial, and we show that this drug is effective. But what you've done is excluded all the people who have multiple diseases or other comorbidities or on other medications at the same time. And now all of a sudden you're surprised that the choice that the literature suggests doesn't necessarily match the outcomes you're observing, because in the real world, people have all those other things. And so the idea is, can we use this real world evidence to help get a better insight in a more precise evidence-based way? So that's the ultimate goal. We're not there yet, but there's a lot of opportunity here, and a lot of people are kind of excited by this idea, both within the healthcare systems and within the pharmaceutical industry for the reasons we talked about before the talk started. But there's also a lot of challenges in trying to do this. In particular, you can think of this road metaphor like Waze or some other navigation app where we're tracking cars and trying to look at where traffic is. The problem is we don't know where the roads are. And that's especially hard given the nature of health data, where you have large-scale data sets, particularly if you want to do this kind of use case that we talked about where we're looking at patients with multiple comorbidities that are the same. You need to have large numbers of patients in order to get to a large enough cohort to be statistically meaningful. And so you're often dealing with tens of thousands or millions of sequences. Each of them can have hundreds or thousands of events if you look at all the things that happen to a patient over multiple years. And most challenging, I think, for visualization and analytics is the complexity of the data, that you have lots of different types of events in your data set, and it's very sparse and irregular over time. So you go to the doctor's office and you might get 20 different things all on the same day, and then you have nothing for 6 months. And then you might have a burst of a new medication and then something else. And it's different for every person. So to give you a sense of scale, I don't know how many of you have worked with medical data before, but you know, of all the data, of all the domains that I've worked in, is by far the most complicated information space that I've ever tried to tackle. And to give you a sense is just looking at diagnosis codes alone. So if you look at how data is represented in your medical record, almost everywhere around the world, there's a standard called ICD, the International Classification of Disease, which is widely used. Version 10 is what's used in the US and in many other countries. And in that version, there are 68,000 unique diagnosis codes. So if you look at all the different things you could be diagnosed with, it's 68,000 of them, each of which could be spread out over a timeline. If you get into procedure codes where you talk about the verbs that people do, the things they do to you, that's another 9,000 or so. Then you have lab tests, medications, and more. You're quickly getting into kind of hundreds of thousands of dimensions. And so if we're faced with this tens of thousands of dimensions, millions of event sequences, billions of individual events, each of those leading to their own outcomes, right? What we want to do is figure out how to tease apart that data and look at it in this mental model that's as intuitive as the different pathways that people travel down and what outcomes they come up with. And so that's led to a journey of several different papers over the years that I'll talk about, and then I'll end with some of our latest work. And so let me kind of step into this. And the first project that really started me down this path is something called Outflow, which is really a naive approach, if you will, really getting started with this problem, where we just wanted to look at all the different ways that people evolved and what outcomes are associated with them. And we applied this to a bunch of different use cases. The picture you see here is from a set of heart failure patients where we're looking at the order of onset of different symptoms and trying to understand if the order in which symptoms appeared related to the eventual health outcome of a patient. And in this visualization, we really just took 3 steps. We did a pre-selection of relevant dimensions. So we had to say which events were we most interested in before we started. And we, in this case, we had 18 different events. So typically we're looking at choosing 10 to 20 at the most. Then we had our approach to kind of aggregating this data into an aggregate representation and then rendering the visualization. So to walk you through this quickly so you understand what you're looking at, after we selected the relevant events that we wanted to visualize, we then created this data structure. Remember, everyone's on different timeline, different amount of time between the events. It's all kind of whenever the symptom appears. So we need to harmonize that across a large number of patients. And so what we did is we took, for a single patient, we'd start on the left, which is they had no symptoms at all. Then at the second step, they had the first symptom, symptom A. Then the second step, the third step here, they have the second symptom, symptom B, then symptom C, and then symptom D. And if we do this for multiple patients and kind of layer them on top of each other, we can start to capture all the permutations. So again, now we have a patient that starts with nothing, and then has B, then A, and you can see they end up at the same state. Right? So these are patients that got to the same place, but through different pathways. And then symptom C, and then symptom E. And we can keep layering on top and kind of capture the full set of permutations within the data set. We can then calculate aggregate statistics for each of these paths and nodes. For example, the number of patients, how much time it took to travel from one to the next, right? How much time was there on average between the symptoms, and what their average outcome was, depending on our outcome measure, if it was mortality or hospitalization or whatever we were trying to analyze. Given this representation, we could then map that to a graph-based kind of layout, where from left to right, we would position things in the sequence of those states. And we would represent each state as a rectangle where the height corresponds to the number of patients. We would then add onto that what we call time edges, which would give you a width, which is the duration of the transition. So if it was slower to move from A to AB than from B to AB, that edge would be wider. And then we would color code them based on the outcome measure. So we could have better pathways and worse pathways based on our outcome measure. And then finally, we would link these together. Now, in this case, it looks pretty simple. In practice, these edges, the graphs get very complicated pretty quickly. And so then we also did a lot of work on layout algorithms to try and minimize edge crossings, to minimize curvature of lines when we laid this out so you could follow pathways as straight as possible. And also to preserve the semantics of ordering. So we'd kind of push good paths to the top. But sometimes these different constraints conflicted, so we have some optimization-based work. But what we got in the end is something that looks like this. And this visualization is the same design we just talked about. In this case, it's applied to a set of heart failure patients where we have some patient similarity analytics. So we have a target patient. We're querying for similar patients based on their medical record, and then looking at the order of medications that were prescribed to them and their association with outcomes. And so I'll pause here and just show that the colors are a little bit different in this green color scale. If you look at this largest path, this fattest path through the visualization, that corresponds to the medical guideline. So the most common path is the actual guideline recommended treatment. But in practice, it's not the only one. There's a lot of variability, as you can see, and it's also not the best outcome as far as what was obtained from these treatments. And so here we've highlighted the one that's kind of at the best outcome after the first step, which is a more aggressive treatment, starting with a step 4 drug instead of a step 1 drug. So you're kind of skipping ahead into a more aggressive treatment pattern. And so with this kind of visualization, we can do a lot of filtering and changing of constraints here. For example, we can adjust the outcome measure to change what we are coloring by, whether it's hospitalization or just death. We can also filter. And so now we've figured out all the pathways that resulted in eventual death by patients who are treated in this way. So that's kind of the first thing that we did. We did some studies that showed it was accurate and people were fast. People seemed to like it. It was intuitive to help them understand things. And so we thought we were happy with that result. It was also something that was commercialized through IBM. This is one of my last things at IBM. And so that is now, was turned into something called Patient Care and Insights, became something called, that's part of the IBM Watson Health portfolio. And it was also deployed at a major pharmaceutical company. Again, that theme keeps coming up. They were looking at data from 100 million patients that they were trying to squeeze through this kind of visualization to understand different niche populations where they could target drug development for cancer populations that were not being served by existing medications. That work, though, highlighted one of the obvious limitations of this system, which is that you had to select the number of events you wanted to do in advance. So we, in that first picture here, selected 18 events. The second picture from Ben Schneiderman's group, they had a different approach for this, but they were selecting only 6 event types. But we talked about having hundreds of thousands of different kinds of events, right? So there's kind of a mismatch in scale. One of the problems is, as you put more events in, is you get this, it's hard to aggregate because everyone is different. And so there was some work from Megan Monroe, also in Ben Steinman's group, about trying to do pattern identification and then substitution. So you'd find a pattern of events and replace it with one event to represent the pattern. But you still had to start by looking at this big, messy set of events. And we had some algorithms to try and collapse similar nodes, but still we're left with this problem of you have to identify a relatively small number of events. And so that motivated the second kind of step in this sequence of work from my team, which was looking at how do we scale up to larger numbers of events where the complexity and the permutation starts to grow. And so the approach we took was to take that event sequence I started with, where we just lined everything up in order of time, and turned it into this 2-tier representation for an event sequence, where instead of just selecting 18 kinds of things and throwing everything else out, we instead select a small number of things as what we call milestone events, the important things, and we keep everything else around as an intermediate event. And then what we can do is apply an algorithm where we basically say all patients, at least to start, have to have the same set of milestones. And we can then split those sequences up into pieces. And then we can group them and start to aggregate just in each of those little subsets into a data representation that looks like this. All right, so now we have this high-level picture where all the patients have the same set of sequences. In this case, it's a 1-year time window followed by angina, so some chest pain, followed by heart failure. And then in between those milestone events, we take all the intermediate events for all the patients and their associated outcomes. And what we're going to do is start to analyze those intermediate events and try and dynamically surface the ones that are statistically interesting to users so they can drive their analysis towards the more interesting things. And so we can calculate, for example, how often a particular symptom occurred, like ankle edema. We can look at how many of the patients with ankle edema had a good outcome, how many had a bad outcome. We can also look at correlation statistics between outcome and those events, and then kind of show that to user to help them pick which of these many events is both statistically interesting, because we're showing you the most statistically interesting ones, but also then you as a user can select ones that are semantically interesting, because there might be something that's very highly correlated. For example, if you filter it to just women, you'll see pregnancy is very highly correlated, but that's not necessarily interesting to your analysis, right? And so we can now combine the statistics with the user-driven selection. And once we find an event that the user finds interesting, we can then manipulate our data structure by looking for ankle edema, for example, in all those intermediate selections. We'll only find ankle edema in some of them, right? Because not every patient has this event. And once we find it in a subset of those intermediate event sequences, we can then analyze our, basically divide our data structure into 3 parts. So we can have, for the people who do have ankle edema, we have before and after. And for the sequences that don't have it, we have this without edge. And so we've turned one edge into 3, and then we can recursively apply the exact same algorithm and recalculate and find, again, the next most interesting events. And if we have this data structure, it's really just a graph with the same basic statistics we had in the Outflow example. And so we can visually encode it in the same way. Right? We can take a graph where the height of each one represents the number of patients. We can flow over time from left to right, and we can encode time between events with the width of this edge and color code them based on the outcome. But now the choice of which events to use to define these branch points is dynamically done at runtime while the user is interacting with the system, as opposed to a pre-selection process. And so here is an example of what this looks like. So a user here is selecting coronary bypass procedure as one of the events they care about. And then the other one they'll choose is heart failure. And we're going to move heart failure to the outcome section. And now we're looking at a time window of 1 year before the coronary bypass. So here's our query. We're looking for 1 year worth of data before the coronary bypass. And we're going to analyze that year's worth of data to see which people eventually develop heart failure. All right, so that goes against the system. It returns a set of patients, and we can start to interactively analyze this group. So you start with this big timeline at the top. Because our query is very simple, we only have the start of the 1 year window and the coronary bypass. Our milestones they're just 2. So you see this big green blob. You can also see the gender and age distribution and this long tail of all the different events that are in our system. And then users can start to click on those individual events to see where they are in this scatter plot on the bottom. And the scatter plot is showing you on the x-axis the percentage of patients with good outcomes that have an event, and on the y-axis the percentage of patients with bad outcomes that have the event. And so if you look at the diagonal, that's basically patients who have are events. Each circle here is an event. So the diagonal is events that have no correlation with outcome. They're equally likely in the good and bad outcome populations, right? And so as you move further away from the diagonal towards the top and the top left or bottom right corners, you start to have a stronger correlation, and the events are statistically more interesting. So the first thing you might notice here is this big red circle, which seems to have the strongest negative association with the outcome. And what we find is that those are patients who have heart failure during the year prior. So people who have heart failure before the bypass are likely to have it afterwards. So that's pretty obvious, but not interesting to us. So we just interactively filter that out, and we've changed our inclusion criteria to narrow our analysis down more effectively. All right, so we've changed our cohort. Now we can continue recursively through this process. Here we're looking at loop diuretics, which is a medication. That's the next and most negative thing. And so we can drop that in as a new milestone, and you can see that one edge turned into 3. Right? We can adjust the color scale here to focus in on the range of outcomes we have. This is a relatively rare event, so the outcome for the overall cohort is only 25%. So we kind of narrowed our precision. Now we can start doing additional analysis of these intermediate time periods. So now I'm looking at before loop diuretics and after loop diuretics. I'm paying attention to this green circle at the bottom that's kind of moving back and forth. And I can see that this anion gap lab test is actually more strongly associated with good outcomes early in the time period for this cohort. And it's still positively correlated later in the time zone, but has a stronger significance in the beginning. But I don't know whether they're the same patients or not. Right? Some people may have it before, some people may have it afterwards. They might be different people, they might be the same. So what we can do is start to drop these in as additional milestones and further subdivide our data set. And we end up with a picture that looks like this. Right? Now, if we click on any of those lines at the top, we can see where these patients flow through the rest of the visualization by doing this kind of overlap analysis. And so the mouse right now is pointed on a group that had the lab test early in the sequence over here, then had loop diuretics, but then did not have that lab test later on in time. But we could see for that subgroup that had the lab test in the beginning, but didn't later on, their outcome was drastically different, right? Very large differences in outcomes. And we can do some statistical analysis to like p-values and stuff to see whether it's to get a sense of how significant that is, but you can see there's a pretty stark difference. And we can do all this by kind of clicking around through the cohort and trying to understand the difference events. All right, so we did again the same kind of user studies, and people were accurate and fast and happy with the interface. We did some additional work where we actually applied this to a data set from a large EHR vendor, again, looking at about 100 million patients to look at diabetic outcomes. And they found some really interesting things, but we also ran into some additional limitations, which are now motivating the work we're doing currently in this kind of area. So I'll talk about a couple of them, but the first thing I'll talk about, and the one I'll spend most of my time on, is the fact that now as we interact with this data set quickly, where we can just intuitively click and drag and apply filters and subset the data, what we're quickly doing is narrowing our data set from very large into much smaller by applying a handful of constraints that look statistically interesting, But all of a sudden, the cohort that we've selected by applying those filters is quite different from the one that we started with, but not just along the dimensions that we filtered. All right. The fundamental challenge is that we've applied these filters based on 2 or 3, maybe 5 different variables, but the data sets that we're working with have 100,000 variables, and they're not independent. So if you apply a filter to one drug, all of a sudden you're also shifting all kinds of other variables in your data set, right? The people that match the criteria who have, in this case, a loop diuretic, they also have a whole bunch of other things that maybe cause them to have the loop diuretic or something else. And so what you end up with is essentially a version of selection bias, right? Where we're trying to generalize from this narrow group of patients that no longer looks like the population we're trying to make inferences about. And so that led to some work which we started in 2016 and is now continuing with one of the major initiative that we're working on to try and understand this selection bias that enters into the equation when we're doing this kind of quick slicing and dicing through the data in a medical context where we're trying to make inferences about a larger population. And really, it's not unique to medical data. It's really anything that we do with visualization. If we're trying to make an inference about what will happen in the future, we have to be aware of those biases that get introduced in our analysis. And so what we've done is we've built some systems that start to track the subgroups over time and build this kind of provenance of the cohort that you're working with, quantify the changes in the underlying distributions across all our data sets, visualize those differences, and in the aim of our main grant from the National Science Foundation is also then to adjust to compensate for it so that we can have essentially a bias-corrected visualization. And here we're talking about selection bias, not cognitive biases, right? So just to be clear of that. But can we adjust for selection bias in the same way that you would adjust a survey that you do on public opinion based on the sample that you reach in your survey? So once again, the motivation here is that when we work with visualizations, we might query based on 5 to 10 variables, visualize 5 to 10 variables, somewhere in that order of magnitude. But the data set we're working with has hundreds of thousands of variables which are not independent of each other. So when you constrain on those 5, right, you have changes in your underlying data dimensions which are invisible to the user because you're not visualizing them. And if you're unaware of them, then you can't account for them in your inferences from the data. And so our general approach is to build this kind of history of the user's analytic focus as it evolves, as I mentioned, which is, in our model, a sequence of data sets, right, or cohorts, with a set of rules about the filtering constraints that have been led from one to the other, which is essentially a version of the interaction that led you to there, right? If you select something and click filter or exclude, you're adding new constraints that modify your cohort. From there, we have a distance metric, which we calculate. I'll skip over the details. I can talk about it if people are interested. But essentially, what we then get is a distance that between every pair of data sets that quantifies how similar the distributions are across all the variables in our data set. And then we can visualize that in the picture. So if you look here, we have the start where we had one cohort, then we led to a second and a third and a fourth. And along the way, you notice the color under this first data set is changing. It started with very green and then started to get yellower. All right, what that's telling us is that as we add more and more variable or more and more new cohorts to this chain, that it's drifting further away from where we started. And in the tooltip, we can start to show you the variables with the largest shift. Right? What are the biggest confounding factors that are kind of being pushed to the side based on your filters? All right, so I'm going to skip this so I have a little more time to show something at the end, but we have a demo kind of showing how this worked. In terms of the evaluation, here we again tried to evaluate this. This time we took our user population into 2 groups, so it's a relatively small evaluation, but it was really interesting. So we had 18 users, we split them into 2 groups, one who was given the system with this tracking of bias as it emerged, and another group who was given the exact same system just with that part disabled so you couldn't see it. All right, so we were actually calculating, we just didn't show it on the screen. And we asked them to do a bunch of cohort selection tasks and also to think about the quality of the cohorts they saw. And both groups had similar accuracy and ability to assess the different cohorts, similar reportings in terms of ease of use. So adding these additional cues didn't make it more difficult to use. But the people who use this adaptive contextualization is what we called it, the information about the selection bias. They did their work a little bit more slowly because they were more careful. They inspected things more closely, and they were more skeptical in their assessment of cohort quality. They kind of recognized problems that were emerging in their data set. And so we saw this as a success in that we slowed people down and made them think about the quality of their data set before starting to draw inferences and write up the paper that said this is what they found, right? They're kind of deeper thinkers about the other possible explanations for what they're seeing. And we have an article that talks about using this in the cancer center system, which actually motivated a lot of the work with an epidemiologist I was collaborating with, who was trying to think about ways that we could collaborate in helping to address a fundamental problem that she sees in a lot of the literature in epidemiology and other population-based analyses, which is you publish this study that has a finding, and then people try and replicate it in their health system, and they see it doesn't work. So the question is why? And her theory, at least, is that a lot of it is based on data that's not representative of that larger group, which seems to make some sense. And so that's part of our way of trying to get into that. Think about ways that visual analytics can help with that. All right, so those are the three kind of systems that I have a lot of slides for, where we're kind of on this journey, starting with just looking at all the permutations, then trying to allow us to look at higher dimensional data, then trying to think about this notion of selection bias and how it comes in. And that's leading to kind of our current research, which is expanding on this notion of selection bias and trying to visualize and correct for it, as well as the project I'm working with Niels that you mentioned earlier in looking at longitudinal prediction and visualization of patient-generated health data. So some similar aspects of these pathways, but our current focus in that NIH-funded work is really on looking at a single patient. So we don't yet have this pathway work done. That is in our research aim, so we'll get to that eventually. And so I have some pictures of some of those systems. And what I'd like to do is flash on the screen for a minute this first project you see here, which hopefully we'll have something at Viz this year, if we can make it by the end of the month. But what we're trying to do is visualize data and take advantage of event hierarchies as a way of tackling another problem that we had when we were doing these pathways, which is, I mentioned this work where we looked at diabetes in this large EHR vendors data set. One of the problems we had is it's great that we can handle hundreds of thousands of events, but the problem is that we often want to group events together. So if you think about 68,000 different ways of diagnosing disease, many of them are functionally equivalent. So you have 20 different ways of representing some subtype of heart failure. But for your given analysis, you would just want to group them as equivalent, right? It's just heart failure. But then for another data set, maybe you really do care about subdividing them in different ways. And so it's not just 100,000 variables, but there are 100,000 variables that have this essentially this ontological relationship between them. And so we're trying to build interactive ways that allow people to navigate through that hierarchy. So let me bring up a new screen here. So I think you see, hopefully, the screen here. And so what I've done here is visualized in our new system a query that looks at 1 year's worth of data before getting a diagnosis of pain, followed by a discharge from the hospital. So those are people who had pain, ended up in the hospital, and were discharged. And the outcome that I'm paying attention to is opiate-related disorders. So people who are essentially have some kind of opiate addiction or other problem like that, all right? And we'd like to try and understand what kinds of events are leading to that. And so we have this visualization here over the left where I can select different periods of time similar to the previous problem. And I get this animated scatter plot. And what I can start to do is look through this data set for different things that are happening. And if I just kind of focus on this visualization here, I can see this event down here, which is nicotine dependence. And if I click on it, it's something that has a strong correlation with negative outcomes. So people who are addicted to nicotine have a strong association with eventually having opiate addiction, which seems intuitive, right? And so if you have an addiction to one substance, maybe you have another one. But what we've done in this visualization is not just looked at nicotine and dependence, but also we can go up the event hierarchy and look at a whole category of mental and behavioral disorders due to psychoactive substance abuse. So there's all kinds of substance abuse in this parent event. And I can see it has an actually stronger association with outcomes than nicotine. So I can start to navigate through the hierarchy. And now I have all the different kinds of substance abuse. I can see nicotine is the most prevalent of these, but it's not the strongest associated with the outcome I care about. I can look at other categories and actually start to drill down into these and explore the whole hierarchy of different event codes and try and figure out at what level of aggregation of these different events do I want to do my analysis. And eventually, if I find one, right, I can explore through the data set and start to add it to my visualization the same way I did in the DecisionFlow one. Well, I'm getting an error here. I started it up before the talk and I think it timed out. So I won't be able to show it. But if I select on that event, it would kind of go to it would add a set of 3 edges like you saw in the previous example, right? And allow you to kind of recursively explore through the data. But what we're doing is allowing you not just to look at those tens of thousands of events, but also to do it at different levels in the event hierarchy to figure out what is the right representation for your analysis. All right. So with that, my last slide, again, is really just a motivation here for a lot of the work I'm trying to do with this cohort analysis work, which is, given a large population of patients, can we map these temporal events that are messy and high dimensional into a picture that allows us to think about what are the different roads patients travel down, and are there ones that perhaps are less common, or the ones that someone wouldn't normally choose, that based on this kind of data, we can redirect those patients down the better path. And hopefully that provides tools that would then allow us to do better health research, better treatment decisions, and in the end, when these are patient-facing, better self-management of our own care. So with that, I'll wrap up, and I think still have 15 minutes here almost to discuss.
Yeah, thank you very much for a very interesting talk. As David said, we have time for a couple of questions.
Right. Hi, David. Thanks for the talk.
Sure.
In your temporal flow graphs that you showed, do the paths that connects the vertical lines also encode information, or are they just proportional to the number of patients?
Let me switch to a picture just so we're looking at the same thing. So in this picture, is that the kind of one you're talking about?
Yeah.
Yeah, so in this case, they just have the height, which is the number of patients, and that's it. The position encodes the sequence, right? So you flow from left to right, but there's no other data other than the actual name of the event. One thing that I didn't talk about, but we kind of simplified in our previous work, is we made it impossible to have concurrent events. So we enforced an ordering on all events. And so what that means is if 2 events happen at the exact same timestamp, we would have some predefined way of deciding which one was first in our analysis. In the latest work, in that new system that I'm showing here, these bars now actually do encode something, so they are color-coded based on the outcome. And you can also look at concurrent events. So in this case, I've selected the pain not elsewhere classified, which is a generic pain diagnosis code. And if you look in the scatter plot over here, we're actually looking at other things that happen at the exact same day as that. And so we are using it to represent that kind of information. So we're now accounting for this concurrent nature of the data.
Okay, thanks. Do you also have an online demo version of your tools?
I do not. It is something that we are interested in doing. We need to, one of the things is we can't show this data that I'm showing you now because of the privacy rules. So we have to put in effort to get an open data set available to show. And so that's something we would like to do, so stay tuned. We'll try and do that.
Okay, thanks.
Okay, more questions? Yeah, I can continue with one. So David, could you tell us a bit more about what you, or how outcome is defined? So you, for instance, color code the outcome with red and green, but if you think of outcome, it's not something that cannot change over time. So you could successfully treat the disease and then you have a relapse, or you still have the disease, but it's kind of under control. So it's more nuanced. How do you deal with that?
That's definitely true. So for most of these systems, we define outcome the way that it's often described with many of the population health researchers that I work with, which is for a given analysis, you define a particular point for the outcome. And so it's often something within a certain period of time, but not as a continuous function the way you describe, though there are analyses where that could happen. So currently our systems don't handle that. We treat outcome as for each patient, kind of our data model is for each patient we have an event sequence and an outcome value, which is in the range of 0 to 1. And so our systems require you to map somehow from the data to this 0 to 1 range. If you have a changing outcome measure, now it's instead of just being a number, it's a function, right, as a function of time. And that introduces some complexities which we don't handle, but it is an interesting use case that's definitely valuable. So the current way is some function of a patient's timeline to get us to a number between 0 and 1. That's the restriction. And so we have an interface that lets people define stuff. Currently, most of our interfaces tend to be binary outcomes because that's often what people care about in a lot of our partners. But in many cases, that's not sufficient. But often we're looking for the occurrence of some event before or after or within some time period. And so that kind of temporal logic has been the focus of our current interfaces.
Okay, and my second question was more about genomics data. So if you think of an event and you look at the genomics data set, so like you make a whole genome sequencing for a patient, then you would have, for one time point, you would have 100,000 events, right? If you would see every gene and the different attributes that you have for that as an event, how would you treat that? Did you look into that?
So I'm having some discussions now with someone who works with a bit of that form of data. We haven't actually built anything yet, and so I guess there are a couple ways you could think about that. So some of the data we have is not time variant, so you can see some of the things over here, like gender and race, health insurance information. Tends to be, the way we treat it is what we call an attribute as opposed to an event. So it's something that doesn't vary. You could potentially treat your genomic data in that way. If you want to deal with changes over time, and you're looking at those kinds of things, then that becomes a challenge that's a little bit different than this, in that the medical data we work with tends to be sparse, right? Whereas with the genomic data, you'll have these long sequences for every patient. And so it starts to become dense. And so I think some slightly different ways of approaching that will be needed. So we don't directly address that. If you turn your genomic data into genetic markers, where you've detected this marker on this date, for example, then that fits very nicely into this kind of workflow.
Okay, other questions from the audience? No? Then I will conclude with one final question. So if you, so most of the techniques you've shown are like Sankey-like representations. And how would you, like if you think of scalability, if you get increasingly big data sets with millions or coming from millions of patients, would you think that the visualization challenge changes, or is it still the same, but it's more engineering to deal with that? But is it also a visual challenge? What do you think?
So I would say it's the millions of patients is not so much the challenge. So we've applied this to data sets that are quite large, and things work well. The thing that becomes difficult, because if you aggregate, you can represent them in the same kind of flow if the flow structure is simple, even if there are a lot of people. The challenge really to me is the complexity of the data space, even with a relatively small number of patients. That's something that then you have to somehow, you can't just aggregate to solve your scale problem. You have to do something different. And I'd say the last couple of challenges that I've been focused on are in that direction, but there's a lot more that we could do. I think the actual scale for number of patients mostly is solved with engineering. I will say, though, that I don't think Sankey diagrams are the best or the only way to do this. And I think there's a lot of opportunity for better ways to visualize the flow of these patients, particularly something that's not captured well in these is cycles. And detecting cycles is also really hard because, again, we don't have that represented in the data, right? We have to mine that out of these sequences. But if you think about patient care, often you get into these cycles where you get into stable periods of time where things repeat, and then all of a sudden things change. And so there's a thread of work that I've done in collaboration with Nan Chao, where we've been applying mining algorithms to try and discover latent stages of disease evolution that might allow us to get to better data representations for this, the evolution of diseases through different stages, which then can feed into other visualization methods that might give us this kind of cyclical nature of how long people spend in a particular stage of disease.
Mm-hmm. Okay. Well, if there are no further questions, then this brings us to the end of our talk today. Our next talk is going to be in April. We have no final date yet, but it will be held by Roman Pflugfelder from Austrian Institute of Technology. He's going to talk about his work on computer vision related projects. And thanks for coming, and we see each other then next month again. Thank you again, David.
Sure, my pleasure. Thank you.
See you soon. Bye.
See you soon.